Hi everyone, my name is Jose Luis Mendez, and I'm a postdoctoral researcher in the Institute of Physics and Mathematics in Universidad Michoacana de San Nicolás de Hidalgo in Mexico. And this is my recent work. This work is about the thermal characterization of suspensions made with nanofluids, suspensions made with nanoparticles in a liquid matrix, which are usually called nanofluids. And in this case, these nanoparticles have porosity. And we want to investigate what is the effect of porosity in the thermal diffusivity and thermal conductivity. For this purpose, we use this technique, this experimental technique that is called thermal wave resonant cavity. And this is the experimental setup that we used. It consists in a lacking amplifier, which sent a sinusoidal signal to a laser driver so that we obtained a modulated laser signal, laser light, which goes to a silicon wafer, which acts as a thermal wave resonator, as a thermal wave generator. And here we have the liquid sample with the nanoparticles. Then we measure the signal at the bottom with a pyroelectric sensor, so that the silicon wafer send different in temperature, gradients in temperature in a modulated way. We can measure that signal in the pyroelectric sensor. That signal is sent to an impedance coupler, and then it is sent to a preamplifier, and again is sent to the lacking amplifier. The lacking amplifier makes an operation between both signals, the sinusoidal reference signal and the measured signal. And we can obtain in this way an amplitude, a voltage amplitude and a phase without noise. And here, finally, we have a stepper motor, which permits up or down the silicon wafer to make measurements at different lengths from the pyroelectric sensor. And well, we are looking for the thermal diffusivity of our liquids, and we can obtain it from the heat equation. Well, the solution of this equation in one dimension is widely sampled under some considerations, and we can obtain an amplitude and a phase, and the thermal diffusivity can be obtained from the slope of these linear equations, where the first equation can be linearized and the second equation is linear. So from the slope and using this equation, here we have the thermal diffusivity alpha, and R is the voltage amplitude that we obtained in the lacking amplifier, and phi is the phase, or the difference in phases between the sinusoidal signal and the measured signal. Well, and we can obtain in that way the thermal diffusivity of our liquids. And we have the plot of thermal diffusivity versus pore radius of the nanofluids. And we can see that the thermal diffusivity increase as the radius of pore increase. This is something unexpected, as the thermal diffusivity or the thermal conductivity of solid materials in bulk usually decrease when the porosity increase. And in this case, we have seen something different. This other plot is the thermal diffusivity versus the concentration. And well, it only shows that this kind of nanoparticles of cerium oxide enhance the thermal diffusivity of the matrix. In this case, our matrix is a mixture of ethylene glycol and polymer in order to have a stable suspension. And then we propose a different quantity that we call pore density, which is the surface area over the pore area. Then we obtain this quantity means the number of pores per gram. And we have in this way behavior with more sense. Yes. So what we need is a density of pores. Yes. And we calculate the thermal conductivity. If you know the density and the specific heat capacity of the filler and the matrix, you can obtain the effective thermal conductivity of the system. And this is needed to use some mathematical model. Then we use the Lewis-Nielsen mathematical model, which is designed to explain and to predict the behavior of liquids with a solid filler, with some nanoparticle or some particle in a matrix, in a liquid matrix. And here we have this parameter A, which gives information about the shape of the nanoparticles in this case. In this case, we consider our nanoparticles spherical. And this parameter phi m gives information about the packing of the nanoparticles. And we mixed this model with another model proposed by Sumirat et al. For nanoporosity. So this model is valid when there is a material which diameter of porous is smaller than this L, which is the mean free path of the phonon. So we use these both models. This K effective was used inside this key M. So we are considering that we have a liquid with nanoparticles inside, but that nanoparticles have nanoporosity. And we saw a good corresponding between the model and the experimental data. This is a simulation of the model. We must to continue working to make the best fit between the model and the nanoparticles. And we can also make a comparison between the Lewis-Nielsen model to this other data of the concentration. And well, summarizing, we can highlight the following facts: that in a bulk material with with porosity. Usually the thermal conductivity decrease when porosity is increased, but in this case of porous nanoparticles in a liquid, we saw that the thermal diffusivity increased with the porosity, and our explanation of this behavior is that as a mass is fixed in these experiments, as we increase the porosity, we are also increasing the number of nanoparticles in these suspensions, so that the thermal diffusivity could increase. But if we define this density of number of porous per gram, we see the expected behavior for porosity, and it can be explained in terms of effective mathematical models. But we must continue working to try to understand this effect of nanoporosity in nanofluids. And well, thank you for your attention for this work.